All right. So yesterday we were kind of going through partial fractions and we talked about all of the cases. So I've got kind of a screenshot of that uh, summary pulled up here. So we said that for partial fractions to work, you need a rational expression where the degree of the numerator is less than the degree of the denominator, meaning it's a proper rational expression. So you have to have that, and then you need to be able to factor the bottom, and you need to factor the bottom completely. And if you do that, what we said is that the denominator, we're going to consider 4 cases of what can happen in the denominator. So you can have distinct linear factors, you can have repeated linear factors, you can have distinct irreducible quadratic factors, and you can have repeated irreducible quadratic factors that are in the denominator. And so for partial fractions, there's a few things that are important about each of those cases. What I've got in green is what it looks like when you factored it out. What I've got in purple is the way you handle the decomposition. So when you're going through and finding A, B, and C, this is how you deal with that. So if it's distinct linear, each one gets its own fraction with a constant on top. If it's repeated linear, every power gets its own fraction with a constant on top, and so on. And so when it's like irreducible quadratic, you get a linear factor on top. So you get ax plus b or cx plus d or something like that. And then what's in blue is then, okay, once we've found a, b, c, d, and so on, then we're going to have an integral to evaluate. And so these are the forms that we're going to use to evaluate those integrals. So if you have distinct linear, we're going to have log forms. If we have repeated linear, we have log and power rule. And then if we have distinct irreducible quadratic, log and inverse tangent, and then repeated irreducible quadratic, we could have a lot of different things mixed into those, but we have power rule, log, inverse tangent, and trig sub. And so that's kind of a summary of all of the cases. What I want to look at today is we kind of looked at an example where you had an irreducible quadratic in the bottom, but there was no middle term, and we kind of reviewed that from before. So today we're going to look at 2 things. One, and actually we're going to do that second. My bad. We're going to look at 3 things. The last thing we're going to do is look at what happens when you have a middle term on an irreducible quadratic. So what happens if you get something where it's ex plus f over an irreducible quadratic, but there is a middle term. And so kind of in reverse order. So we're going to do that last. Right before that, we're going to go through what happens if the degree of the top is not less than the degree of the bottom. So we need to be able to handle those cases. And then before that, I just want to look at a general decomposition problem. And so we're going to start with that first. But any questions kind of on the overview of what we've been doing? We started partial fractions last week, and then we worked a lot more on it yesterday, and you have a ton of practice problems if you want them. All right. Any questions so far? Okay, my bad, I don't have the chat pulled up, but I will pull that up now. So if you do have a question that you want to type in chat, you can. Okay, so the first thing I want to do is just kind of go through a huge problem where we write out the form of the partial fractions decomposition. Of the following. So just the write out form of the partial fractions decomposition. Do not solve for A, B, C, etc. Okay, and so we're going to do one where we have this huge fraction. So this is the problem. So if we have, say, 2 over x to the third times 5x minus 1 times 3x plus 1 squared times 9x squared plus 16 times x squared plus 2x plus 5 to the third. And so this is just a question of getting, okay, how do you, once you have a rational expression and you have factored the denominator, if you factor it into this, which is ridiculous, we won't deal with any that are that large, but if you did factor it into this, kind of what are all the things that can happen? And so how do you set up the A over whatever, B over whatever, CX plus D over whatever? How do you set that up for this? And so when we do that here, we treat x to the third as a repeated linear factor. And so we talked a little bit yesterday about when you have x squared or x to the third, we're going to look at that this way. And the reason we're going to do that is because x squared, even if so obviously this is x cubed, but if it was x squared is not considered irreducible because there is a root for it. So x squared has a 0 of 0. So the root is 0, 0. The x-intercept is 0, 0. So it's not irreducible, and it's the linear factor x, and it's there twice. So for partial fractions, we think of it that way. Same deal with x cubed. So we think of it as being the linear factor there, but it's there 3 times. So for the x cubed part, we write the answer to this as a over x to the first plus b over x squared plus c over x to the third. Does that make sense to everybody? Any questions on that? Okay, and then when you have 5x minus 1, you put d, that's linear. It's distinct, so you don't need to repeat anything. But you have d over 5x minus 1. And then you have 3x plus 1 there twice, so that's still linear. So we're going to put e over 3x plus 1 to the first and f over 3x plus 1 squared because it is linear, but it's a repeated linear factor. So you put all of the factors from all of the powers from whatever the biggest power is down. And so this is squared, so we're going to put 2 and 1. And the idea is both of those could contribute to this being in the common denominator. Okay, and then 9x squared plus 16 is an irreducible quadratic. So we're going to put gx plus h over 9x squared plus 16. X squared plus 2x plus 5, we need to make sure that that's an irreducible quadratic, but it is. The way we make sure of that is we check the discriminant of the quadratic formula, so b squared minus 4ac. Here that's 2 squared minus 4 times 1 times 5, which is negative 16. And so because that's negative, we know it's irreducible. It's repeated, so we get ix plus j over x squared plus 2x plus 5. We get kx plus l over x squared plus 2x plus 5 squared. And we get mx plus n over x squared plus 2x plus 5 to the third. And that's it on this. We could then go through and solve for a through n. That would take probably several hours or several days to figure that out. But anyway, we won't do that. But that is the general setup. Does that make sense to everybody? Any questions on that? Okay, so that's just kind of getting at the idea that we're talking about up here in purple, that this is how you break down each of those cases. This is one where all of those cases happen to show up somewhere in that problem. Yeah, so Andy, somebody in chat asked, can you explain the b squared minus 4ac? So to determine that a quadratic is irreducible. So irreducible means that it doesn't factor even if you allow for square roots. And so like yesterday we were talking about x squared minus 7. In algebra, you would have said that's prime. But in calculus, we would factor that to x plus square root of 7, x minus square root of 7. And so we allow for any real number when we're doing factoring for this, for partial fraction. So we probably don't want to do a problem with the x plus square root of 7, x minus square root of 7, but we could. And so when you're doing these, to make sure that it's irreducible, this needs to be negative. That's what determines that it won't factor even if you allow for square roots. If that's positive, then we would need to factor it further. So like if this was 9x squared minus 16, or if this was x squared plus 2x minus 5, those things would factor, and we would need to use the quadratic formula or square roots maybe to do it in some cases. Here, if it was 9x squared minus 16, we wouldn't, but we would factor that down and they would actually become linear factors or maybe repeated linear factors. All right. Other questions so far? The quick answer to that is if that's negative, that's what means that it's an irreducible quadratic. All right, if the b squared minus 4ac is negative. Any other questions so far? You guys good? Okay, so then we're going to look at the next question, or this problem. So we have 2x cubed plus 5x squared minus 11x minus 9 over x squared plus x minus 6, and we're doing the antiderivative of that with respect to x. And it looks like the partial fractions problem, but the big difference is what? So what is different about this one from the other ones?
The degree on the top is bigger than the degree on the bottom.
Yeah, the degree on the top is bigger than the degree on the bottom. And so when that happens, or even when they're the same, so if this had been x to the third on top and x to the third on bottom, or if they were both x squared, then we need to do something else first. And what we do is we do long division. So we divide the bottom into the top using long division. And so there's a lot of steps to this, but we're going to review that quickly. So we're going to do x squared plus x minus 6 into 2x to the third plus 5x squared minus 11x minus 9. And this is something that you should have learned at some point in algebra. If you did not, and you need more practice on this, this would be something to maybe talk about at the review sessions tomorrow. So if you want to do another one with long division, we can do that. But we're going to kind of go through it quickly. There are 4 general steps to long division. You divide first, you multiply second, you subtract, and you bring stuff down, and then you repeat those kind of 4 steps. So they're the same 4 steps as division with whole numbers, but they're a little more complicated with polynomials. And this is just an easy review for you, but I want to talk about this. Go through this one in pretty much detail. So when we divide the first term divided by the first term. So on the division step, you ignore everything except the first terms of whatever you're dealing with. So here we're going to take 2x to the third divided by x squared. That ends up being 2x. All of the division answers go on the top of this, and they should line up with the power that you're dealing with. So this is 2x to the first. We're going to line that up with x to the first. So everything in a long division problem should line up. So anything with x to the third should go above or below that, x squared above or below that, x to the first same, and then any constants above or below that. So we get 2x. Now we're going to multiply. And when you multiply, you do the 2x, whatever you just got, times everything out here. So 2x times x squared is 2x cubed. And we write that in the x to the third column, but we write it down here. 2x times x is 2x squared. We write that under the x squared. And 2x times negative 6 is negative 12x. Okay, so that's the multiplication step. Everything should line up. So if we were skipping a power here somewhere, so like if there were no x squared term, you would 2x times negative 6 would still go here, and maybe there would be nothing under that. That's okay when that happens, but you do make sure everything lines up. Now you subtract. And so somehow indicate that you're subtracting everything. So I usually just make a big minus sign, meaning I'm going to subtract not just the first terms, but also these. So 2x cubed minus 2x cubed is 0. But now it's 5x squared minus 2x squared. Well, that's 3x squared. And then where it's a little bit easy to mess up is that here we're doing negative 11x minus negative 12x. Well, that's minus negative, so plus positive 12. So we get plus 1x there. And then we get minus, I'm sorry, so that's the subtraction step. And then bring down means you bring everything else that's left down. So we're going to bring down the minus 9. Or you can think of that as subtracting 0 either way. So maybe it's just all one subtraction step, but same idea. All right, questions to there? Not done yet, but everybody good? Okay, so then we go to divide again, and we're going to divide the first term that we're dealing with now, so 3x squared, divided by the first term in the divisor. So we do 3x squared divided by x squared. That's 3. The division answers again go on the top, but they line up with whatever power of x we're dealing with. Well, that's x to the 0, so we line it up with the 9, which is also x to the 0, and we put a sign with it. So if it's plus 3, obviously, or if it's 3, put plus 3. If it's negative, obviously put minus instead. Now we're going to multiply again. So 3 gets multiplied by everything out here. So 3 times x squared is 3x squared. 3 times x is 3x. And 3 times negative 6 is negative 18. Now we subtract. 3x squared minus 3x squared is then 0. 1x minus 3x is negative 2x. Negative 9 minus negative 18, that's plus positive 18. So we get plus 9 there. Questions to there? Okay, so now you actually stop, and the time that you know to stop is whenever you're down here, when the degree of this is less than the degree of the divisor. So like when we got down here, we had 3x squared, the degree here is 2, the degree here is 2. They're the same, so you keep going. If it's less, then that's when you stop. So this is now degree 1. That's less than the x squared degree, which is degree 2. And so now we stop. This is called the quotient up here. So 2x plus 3 is the quotient. This is the remainder, negative 2x plus 9. What that's actually telling you is that the original fraction, the division that you're performing, so 2x cubed plus 5x squared minus 11x minus 9 over the divisor, x squared plus x minus 6. Based on this, that is equal to 2x plus 3 over, 2x plus 3 plus the remainder, negative 2x plus 9 over the divisor, x squared plus x minus 6. Does that make sense? Okay, so now we go to this original problem, and the point of the long division for our calculus problem is that we now can rewrite this in that last form. So we can rewrite it as 2x plus 3 plus this other fraction, negative 2x plus 9 over x squared plus x minus 6 dx. And that's all in parentheses. Okay, why is that now helpful? So there's still a lot to do, unfortunately, for this problem, but what do you think maybe we should now do for this? What do you guys think?
It's separated.
Fraction.
Yeah. Yeah, we're going to separate it. And so you're going to have the integral of 2x dx, the integral of 3 dx, and then this integral. And if somebody else said partial fractions, you will do partial fractions on this now fraction. So we're going to separate it first. So we're going to get 2 integral x dx, because that one's easy. We get the integral of 3 dx. That one's relatively straightforward as well. And then plus the integral negative 2x plus 9 over x squared plus x minus 6. Now this is partial fractions. The degree of the top is smaller than the degree of the bottom and the bottom factors. So we're going to come down and do partial fractions on that. So I'm going to draw a line. And we're going to do all the partial fraction stuff down here. So negative 2x plus 9 over, and that factors to x plus 3, x minus 2. Everybody clear? Okay, these are both distinct linear factors. So we write this as a over x plus 3 plus b over x minus 2. The common denominator is x plus 3x minus 2. So we multiply by that over 1. On the left, that gets us negative 2x plus 9. On the right, that gets us a times x minus 2 plus b times x plus 3. And now we solve these. And so we combine like terms like we've been doing now for a couple days. And we get it to here. All right, now I know I did that part fast, but are there any questions on it? So we kind of went through the rationale of that more slowly the past couple of lectures, but is everybody clear? All right, and so based on that, we have a plus b is equal to -2. And then -2a plus 3b is equal to 9. And now you can solve this a lot of different ways. I would probably look at that, or I do look at that and immediately think, let's multiply the top one by 2. Whoops, but let's actually multiply the whole thing by 2, so that's -4. And then write the other one underneath it. So now if we add those, the a's fall out, so we get 5b equals 5, so b is 1. And now a plus 1 is -2. So a is -3. Questions?
Baby, I'm in class. This is
Oh,
important.
sorry.
It's okay.
Bye.
I'll call you.
All right. Sorry. Questions? You guys good? All right. So then we're going to rewrite this now as a over x plus 3. So -3 over x plus 3. And then plus b over x minus 2, and b was 1. So 1 over x minus 2, and I just went ahead and split that into 2 integrals. And carry, obviously we could go ahead and do these if we wanted to, but we'll carry those down just so we're focusing on that step. All right, so we get it to here, and now we've got 3 integrals that we can handle, or 4 integrals that we can handle. Everybody good to there? All right, so integral of x dx is 1/2 x squared, and that cancels with the 2, so we get just x squared plus 3x minus 3 natural log absolute value of x plus 3 plus natural log absolute value of x minus 2 plus c, and that's the answer. A lot going on in that problem, but the new part is having to do this long division first. That lets you rewrite the original problem, and then this became like what we were doing yesterday and the day before that or last week. And so you do the partial fractions. In general, this could be any of the cases we were talking about before. So like this might be irreducible, or maybe it factors into an irreducible quadratic and something else. So all of that type of thing can happen. But the idea is when you have the degree of the top larger, or if the degrees are the same, you should start with long division and rewrite the problem. There are a few exceptions to that. So like if there's a quick U sub that works or some small manipulation you can make, you can get around this, but that's rare. So those problems are set up that way normally. When the general approach, when the degree of the top is bigger or when the degree of the top is the same, is to start with long division. That gets you a polynomial that's not in a fraction at first. So like something x plus something, or maybe x squared even, or just a constant or whatever. And so you get this polynomial, and then you get a fraction for the remainder. That fraction generally would be partial fractions, but it's whatever you do from that point. All right, but at least it's in the form where you can use partial fractions because the degree of the top is smaller, assuming the bottom factors. All right, any questions on that example? Like I said, there's a lot going on, so feel free to ask. Everybody good? All right. Okay, so kind of what we want to talk about today is just the general decomposition. So how we deal with that. We want to talk about what do you do when the degree of the top is bigger or if the degree of the top is the same. And now I want to talk about what do you do if you have an irreducible quadratic in the bottom and if there's a middle term on that irreducible quadratic. And so yesterday, the last example we did in the video, we did one where you had an irreducible quadratic. It was after doing partial fractions, but the irreducible quadratic, I think it was 9x squared plus 16 or something like that. and there was no middle term. And you ended up using log and inverse tangent for that. And that's actually what we're going to do here. But I want us to notice two things about this. One is that the bottom does not factor. So if you're trying to come up with two things that multiply to 52 and add to -8, there are no real numbers that do that. And so there's no way to factor that. We can check to make sure, and we should check to make sure that this is actually irreducible and that we're not just missing the factorization. The way we do that is to do b squared minus 4ac. And so you get -8 squared minus 4 times 1 times 52. And that's 64 minus 204. And it doesn't matter what that is, except that it is negative. And so because that's negative, now we know it for sure it's an irreducible quadratic. That means we're going to do this problem directly. That way we're not going to use partial fractions decomposition, but you could get that out of one of these. So like it could be one where you're solving for a, b, c, d, and so on, and maybe it's like ex plus f over whatever we just got, and e would be the 3, I think, and yeah, so this would be like ex plus f, e would be 3, and f would be -5. So this could come out of a larger problem where we actually did use partial fractions, and now we're going to solve this problem. Technically, what we're going to do on this problem is not partial fractions, it's actually just u sub, but it's a lot of creative algebra. Okay? All right. Questions so far? Everybody good? Okay, so like I said, this could come out of a bigger problem. If it did, you would just do this on that part of the problem. The other thing is make sure it's irreducible. And the way you do that is, okay, it is quadratic, so x squared, and then b squared minus 4ac is negative, and so that means it is an irreducible quadratic. Okay, when that happens, then it's going to be log and inverse tangent. And so what you do is you start by trying to make it log. So if it's log, what would u have to equal? So the log form is 1 over u du. What would u need to equal to make it match the log form? Yeah, what do you guys think?
The denominator?
Yeah, u would be the denominator. So u would equal x squared minus 8x plus 52. And then du is 2x minus 8 dx. And now normally we would say, okay, that's going to be too hard to get out of here, but it turns out it does work. And so we're going to do a lot of manipulation in order to get the 2x minus 8 on the top. Okay, so we're going to do that in a couple steps. One thing we're going to do is we need to change the 3 to a 2. So I'm going to factor the 3 out and make it x minus 5/3. It's important that the 3 has to come out of the 5 as well as the 3x. And now we need 2x instead of x. So we're going to multiply inside by 2 and outside by 1/2. But when you multiply inside by 2, the 2 distributes, so you get 2x minus 10/3 over x squared minus 8x plus 52. All right. Questions to there? Okay, so now we need 2x. We've got the 2x, but we need 2x minus 8 instead of 2x minus 10/3. Why would it be a mistake to like try to factor the 10/3 out or try to multiply this by something to get the 8 that I need? What would be wrong with that here? You could
Change the 2.
Yeah, it would change the 2 that we already got. So anything you're factoring out or multiplying this by, you would also mess with the 2. Well, we already got the 2. So to get the 8, what we do instead is we subtract 8. And so I'm going to do this in red. We'll go ahead and make that 3/2. So we have 2x minus 10/3 over x squared minus 8x plus 52. And now we're going to put in the 8 that we want. Now you're for sure not allowed to subtract 8 from a problem at random. But if you subtract 8 and then add 8, Now that's okay because -8 plus 8 is 0. And so if I canceled the stuff in red, I would get back to what I started with on the last step. Does that make sense? Okay. Why is that helpful? What can I now do, and what am I even trying to do with this? So the goal is to get it to be 1 over u du. How can I get it so that it is 1 over u du? What do you guys think? It's tricky. Any ideas? Go ahead.
You can move 2x minus 8 out of the fraction beside dx.
Yeah, kind of. So you want to kind of separate this out. This is going to be for the du. But now I don't want this at all. Does everybody see that? So I don't want this -10 plus 8. So what I'm going to do first is I'm going to split this into two integrals where I put 2x minus 8 over the bottom. And then a separate integral where I put -10 plus 8 as the numerator of that one. And now this first one, because of what Jordan was saying, is that you can now move that 2x minus 8 over. This first one is 1 over u du. But now we have this integral to deal with. And it's a lot like the one we started with. Why is it, what is significantly different about this integral from the one we started with, though? So it looks a lot like it, but what's the significant difference here?
It doesn't have x?
It doesn't have x in the top, yes. So because you have a constant over an irreducible quadratic, then it is significantly different from the other. So I'm going to take a step and do what? -10 plus 8. We'll just kind of jot that down on the side. So -10 plus 8 is the same thing as -10 plus 24, which is then 14. So we're going to factor the 14 out, and we're going to get plus 3/2 times 14 integral, and then that'll reduce to 7. But integral of 1 over x squared minus 8x plus 52. Now, when you have this form, 1 over u du, in that form, du, the derivative of u is in the top. So if u is a polynomial, the du, you can write it like this, du over u. The derivative is 1 less power, 1 less degree than the bottom if u is a polynomial. So when this is quadratic and this is linear, we can mess with it to match this form. You have to mess with it a lot, but you can mess with it to match this form. When the bottom is an irreducible quadratic, but the top is a constant, this is the form that we have. 1 plus u squared is the easiest irreducible quadratic that exists. It doesn't have a middle term, and both of the coefficients are 1. So that's an irreducible quadratic where the top is a constant. We're going to have to force this to match that form. That's harder, and I want to take a break from this problem. So if you're keeping notes, leave some space to finish this problem because there's still a good bit left to do. But I want to talk about some weird algebra stuff for a minute. So does everybody remember how to simplify, that'll work. How to simplify x plus 6 squared, I'm assuming yes. What does that simplify to? X squared plus, we do know that, right? X squared plus what?
36.
Plus 12x plus 36, okay. So if we don't know the shortcut for that, the quick way to do it is you square the first term, you square the last term, that's the first and last term, but then the middle term is these multiplied together, so 6x times 2, because when you expand it, you get 6x plus 6x. So it's the 2 in the middle multiplied together times 2. So real quick, what is x minus 10 squared? That is x squared, and then the last term's 100 the middle term is minus 20x because it's two sets of negative 10x. Does that make sense, everybody? Everybody clear? Okay, so then what I want to know is, okay, if we had a problem like that, and it starts as this, okay? So something squared is x squared plus 16x, and then there's a third term, but I'm not telling you what it is. Which problem like this did this come from? So like x plus 6 squared gets you this, x minus 10 squared gets you this. What squared gets you these two? What do you guys think?
X plus 8.
Yeah, x plus 8 squared. So x plus 8 squared gets you x squared plus 16x, but it also gets you what other term? What's the third term?
4.
64, good. Okay, now let's do that again. Does everybody follow what I'm asking there? So let's think through this again. So if I have something else squared, and I get x squared minus 14x, and then some third term, but I won't tell you what it is. If it's x squared minus 14x, then okay, what did this come from?
X minus 7.
X minus 7 squared. And what is the third term then?
49.
49, good. Does everybody follow that? You guys good? Okay, so if I have something weirder where I have this is not a perfect square. So let's say I have x squared minus 10x plus, we'll say 41. Make sure, yeah, okay. X squared minus 10x plus 41. So if I have that, then that's not a perfect square because 41 is not a perfect square. But x squared minus 10x is the beginning of one. Does that make sense? Okay, so what perfect square is x squared minus 10x the beginning of? Like what of this does x squared minus 10x start out for?
X minus 5.
Yeah, so what we're gonna do is we're gonna force x minus 5 squared in. So x minus 5 squared is not the same, whoops, let's not write it that way. We're gonna skip a line and we're gonna write x minus 5 squared. And what I want you to do is I want us to force this expression into here. But x minus 5 squared is not x squared minus 10x plus 41. It's x squared minus 10x plus what?
25.
Not 25. So what we're going to do is from this first step to the second step, we're going to add in 25 because I want one of these to show up. Now I can't randomly add in 25, but I can if I add 41 and subtract, I'm sorry, if I add 25 and subtract 25. Does that make sense? And that is 41, not 45. Make sure that's clear, that's a 1. And so, man, one more time. 41. I'm struggling, but well, all right. And so that now, the first step is equal to the second step. Does everybody see that? Okay, so x squared minus 10x plus 41 is equal to x squared minus 10x plus 25 plus 41 minus 25. Those are equal to each other. This is not yet equal to this, but these three terms factor into x minus 5 squared because we forced that to happen. What could I write here plus what or minus what that would make this second step now equal to the third step? What do you guys think?
Plus 16.
Plus 16, good. Okay. Now let's do that weird thing again. So we're trying to force one of these into the problem. Does that make sense to everybody? Okay, we're trying to force one of those into the problem. So let's say I have x squared. We'll say plus 16x plus 100. Okay. Now that's actually close to a perfect square, but it's not because even though that's 10 squared, this is not 2 times 10, so it's not a perfect square. But x squared plus 16x is the beginning of what perfect square? X plus what? Or x minus what squared?
Plus 8.
Plus 8. So x squared plus 16x is the beginning of x plus 8 squared. We're going to force that in. X plus 8 squared is x squared plus 16x plus what third term? Scroll up because the answer was on the screen. My bad.
26.
plus, well, plus 64, and then it ends up being 36. So we're going to insert the 64. The 100 stays there, and then we got to subtract 64. So now this first line is equal to the second line. But now these three terms become, or can become, x plus 8 squared. 100 minus 64 is, whoops, not equal, but then plus 36. Does that make sense to everybody? Everybody good? Okay, now, that's weird, but the reason we're going to do that is because it takes a quadratic that has a middle term and gets it into the sum of two squares where there's not really a middle term. And so that's what we're going to do back here on this to force inverse tangent to work. So we're going to go over to the side. And we're going to do this process that we just did. So we're going to take the x squared minus 8x plus 52 and think, okay, x squared minus 8x is the beginning of a perfect square. Which one? It's the beginning of what squared? Just like we were doing down there. X squared minus 8x is the beginning of what?
X
Fine.
minus 4.
Yeah, x minus 4 squared. So, okay, we're going to manipulate this to force in x minus 4 squared. Well, x minus 4 squared is x squared minus 8x plus what? 16. And so we're going to add in the 16, but we're also going to subtract 16. And now those two lines are equal to each other, but the third line's not yet equal to the first two lines. Does that make sense? Okay, now 52 minus 16 happens to be 36. And so then this is equal to x minus 4 squared plus 36 because these three terms become x minus 4 squared. Does everybody follow what's going on there? Okay, so two questions about that. One is, what is this process called? Does anyone know? You learned it in algebra, maybe not this way. Starts with a C.
Completing the square.
Completing the square. So this is called completing the square. All right, and so if you learned it a different way, okay, but be able to go from here to here. And then second is the reason it's important, I'm going to answer this part. The reason it's important is because we're going to now replace this denominator with that. We don't want to do that over here, but we do over here. So the next step on the integral is that first one we're pretty much done, so we'll just leave it. And then on the second one, the 14 and the 2 cancel and the 3's cancel. So you get 7. But then we're going to rewrite the bottom as 36 plus x minus 4 squared. And that's because based on that work on the side, that polynomial is actually equal to this. And if you multiplied it out, that is the case. You'd be able to verify that. All right, why would I write it in this order and why is this helpful? What are we trying to do with this? We're trying to match what form?
1 plus u squared.
Yeah, we're trying to get it to be 1 over 1 plus u squared. Well, we've got 1 over. We're going to make it 1 plus u squared. So what should I now do to get it so that it's 1 plus u squared?
Factor out the 36.
Factor out the 36. So we get 3 over 2. And at any point, you can just make that log of absolute value of u if you want. But we're going to factor the 36 out from the bottom. So it's 1 over 36. And then we get 1 over 1 plus 1/36 x minus 4 squared dx. Now, we want this to be 1 plus u squared. We already used the letter u, so we're going to use the letter v. But v is whatever you square to get this. So I want you to take a second and write down on your paper what you think v should be. And if you're wrong, fix it with me in a minute. But remember, this is 1 plus u, or in this case v, 1 plus v squared. Okay, so V should be 1/6 times x minus 4 because it's whatever you square to get this. Does that make sense to everybody? Okay. dv then is the derivative of that. Remember, we're not doing parts, we're doing u sub, just using the letter v. So dv is just the derivative of that, and it's 1/6 dx. And so now we've got 3/2 integral 1/u du. We've got 7/36. We need a 1/6 inside. So then we need a 6 outside. That then gets us 3/2 integral 1/u du plus 7/6, because the 6 cancels with 36, times the integral 1/1 plus v squared dv. And now they're finally both in the form that we can do, where we have log and inverse tangent. So we get 3/2 natural log absolute value of u plus 7/6 inverse tangent of v plus c. U is x squared, u is way back up here, x squared minus 8x plus 52, so on the top left. And you could actually drop the absolute values if you wanted. I think WebAssign doesn't like that, so I'm going to keep them. But you could drop it because it's all positive. X squared minus 8x plus 52. And then, I've got to scroll up. And then inverse tangent of v, or 7/6 inverse tangent of v, so plus 7/6 inverse tangent of v, but v was x minus 4/6, or 1/6 times x minus 4 plus c, and this is the answer to that problem. Man, quite a bit on that question. So there is everything we did. The stuff in red isn't really part of the work, so we're going to erase that, and the part in green, hopefully we're doing that in our head. So I'm going to erase that as well, but or doing that on the side, that's fine, but it's not really part of the main problem. Everything that I've got written here is part of the problem that we should show as part of that solution. There is a lot to that. Questions on it?
Would one of these be on the exam?
Yeah, that is a good question. Normally it would be fair game. Given that it's Thursday, it's unlikely, but let me answer that tomorrow during the review sessions. Okay? All right. Other questions? But to answer the question fairly, this for sure has been on exams on this content before. If the exam were next Monday, I would say for sure fair game if it was next week. Given that you have until Thursday, I'll probably not put it on the exam this time. Is that fair enough of an answer to everybody?
Yeah.
All right, so let's go with no. But by the final exam, good chance. Okay. So the thing about this problem is, okay, yes, this is not a lot of fun, and it's a lot of it's complicated algebra that we're doing. But once you, it's kind of like trig sub. So trig sub problems also were very involved at first, and they're still very involved. But once you do a bunch of trig sub problems, most of them are the same. The middle part can be a little different from one to the next. These are all the same. And so if you do another one that has an irreducible quadratic in the bottom, this is pretty much the same thing every time. So doing 2 or 3 of these, they don't change at all. The one yesterday, if you go back and look, was like this, but there was no middle term, so you didn't have to do the completing the square. You did have log and inverse tangent. That is more than fair game for the exam. The completing the square part will probably avoid this week just because you only have 2 days. But once you get this down, this is the same thing every single time. Okay, other questions so far? Questions on what's going on?
Are we going to work through another example of this?
We are not, because I'd rather you spend your time elsewhere, Abigail. But if you want to focus, if you want to do another example like before the final exam, I'm happy to do that. Or even at the review session tomorrow, that's fair game because not every instructor's exam is the same this time. So that would be fair. Is that fair enough, Abigail? And then if you actually watch, so if you guys go on to that YouTube channel where we post all these videos, there's a video, man, I'll try to find which video it is, where it's me pre-recorded. So I did the video, but it wasn't to any audience. There was no live class during the time. And I did one, and I would be shocked if it's exactly this one, because I just made this one up a half an hour ago. So if it is the same one, sorry, I would not think it is, unless I just happen to make up exactly the same thing. But there's another one where I would work it out on the camera, I'm sure. And I'll try to find that video and let you guys know which one it is. Okay. Other questions so far? That's good. Okay. So on, whoops, that's the completing square stuff. All right. So on the worksheet that you've got, so remember there are 2 partial fractions worksheets. And technically that last problem, not partial fractions, but it's could come out of a partial fractions problem. So on worksheet 1, so partial fractions 1, number 4. So I've been telling you up till now to skip number 4. It's because it's one of these. So the denominator is an irreducible quadratic. And so you have one with the answer. There are also probably examples on partial fractions 2. So this is the one where you do completing the square. But remember, you should do all of them, 1 to 8 on that one for sure, for practice for the exam. I'm not collecting that on WebAssign or on CrowdMark. You don't have to hand it in, but that's the minimum practice you should do on partial fractions to be prepared for the exam. On the second worksheet, I'm trying to look at it. Let me pull it up real quick and see if there's a completing the square one on there, but I kind of think there is. Let me see if I can find it real fast. And actually, you know what, let's share it and see if we can figure it out together. So one thing is knowing that it is this. Okay, so if we look at this worksheet, here's an irreducible quadratic on problem 5, but it does not have a middle term. So that's going to be log and inverse tangent. Number 4 is not. Why is number 4 not like that one?
Did you factor the bottom?
Yeah, you can factor that to 5x plus 2, 5x minus 2. So it's just a simpler partial fractions problem. So you'll do like a over 5x plus 2, b over 5x minus 2. This one is irreducible, so you do log and inverse tangent, but it does not involve completing the square. If you look at 6 and 7, and one thing you'll notice on worksheets, you probably already have noticed, is if you are doing the worksheets, I'll put problems next to each other that I'm purposely doing that where they look almost the same. And there's a big difference between them, and I want you to notice the difference. On number 7, the bottom factors. On number 6, the bottom is irreducible. So b squared minus 4ac, that's 64 minus 100, and so that's negative. And it's not good. Okay, I was making sure it's not the same as the one we just did, but it's very similar to the one we just did. So number 6 is just like the problem we've got, and you've got the answer to, or we just did, and you've got the answer to it. 7 is partial fractions because the bottom factors. So these are problems worth looking at. I mean, the only reason I'm not collecting is because the test is this week. These are problems you should do. It's just if you know you're comfortable with this and need to focus other places, you can. That's why they are optional, but you do have the answer to those. I'm happy to work them with you guys in the review session tomorrow, or actually right now. I've got about probably 15 minutes or 20 minutes before I have to go get ready for my next class. But that is it for today. So if you do have questions and you want to work a problem or two in the next 15, 20 minutes, let me know. If not, I will see you guys hopefully tomorrow at the review sessions. Good luck on the exam, you guys.